negative infinity to negative 1, I think I'll choose negative 2. From negative 1 to 0, I'll choose negative 1/2. From 0 to 3, I'll choose positive 1. And from 3 to infinity, I'll choose 4. And so you can choose any value you want as long as it lies within the interval. So what we want to do is we want to take those values and we want to plug them into our first derivative. Okay, we're going to plug them into our first derivative. And so in this first test value, negative 2, I'm going to be plugging it in anywhere, in any form of this first derivative is fine. If I plug it into the factored form, it seems like it's a little bit easier to calculate. So if I plug negative 2 in here, I'll get 4 times 10 is 40. So that's positive. If I plug negative 2 in here, I'll get negative 5. And if I plug negative 2 in here, I'll get negative 1. So ultimately, we just want to know what the sign is, positive or negative. So this is positive, negative, and negative. And when I multiply a positive times a negative and another negative, I end up with a positive. Okay? So we found out here that the first derivative is greater than 0 in that interval. Testing the next interval, I'll take negative 1/2 and I'll do the same. And I've already done this ahead of time, so I'm not going to show all of the arithmetic here. But once again, I'm just going to take negative 1/2 and plug it into my first derivative and find out if that gives me a positive or a negative value. And in that second interval, I get a negative value. In the third interval, when I take 1 and plug it into my first derivative, I also get a negative value. And then in my last interval, when I plug 4, I get a positive. Alright, so this tells us a lot about the local minimum, the local maximum, as well as where the function is increasing, decreasing. So I'm just going to take this and move on to my next sheet of paper here so I can keep working. But I'm going to transfer that number line, or the intervals. So it's easiest probably just to work with the number line. Negative 1, 0, 3, and we had a positive in this interval, a negative, and then a negative, and then another positive. Okay, so for my local extreme values, my local extrema, I'm going to get a local maximum or a local minimum wherever my increasing and decreasing is changing. So again, here we're talking about the first derivative. And so what's happening here is that it goes from increasing to decreasing, and I get a local maximum. Here it goes from decreasing to increasing, and I have a local minimum. So let's use our little sign chart here to help us figure out what we have and where. So at negative 1, what's happening is that it's starting off increasing, and then at the value negative 1 it changes to decreasing. So when that happens, we get a local maximum. I should specify local maximum. And that occurs at negative 1 something. And I can actually look back to part A where I did my absolute extreme test to find out what the y coordinate is at negative 1, and it looks like it was 7. But the key here is the negative 1 piece. At x equals negative 1, we have a local maximum. You can see between these two intervals we don't have a sign change, so we don't have any peaks or valleys, but we do have one here. It's decreasing, and then when it gets to negative 3 it starts increasing. And so we have a local minimum at that point. At positive 3, and then if I look back to see what my y value was, it was negative 185. But again, the x part is what we're really interested in. That's where the local minimum and the local maximum values occur. Now, Based on that same information, we can also write the intervals of increase and decrease. So basically, the signs that we see on our number line correspond directly to those intervals. So from the interval negative infinity to negative 1, I can look at my sign and see that it's positive. The first derivative is positive, which indicates that the function f itself is increasing over that interval. From negative 1 to 0, it's decreasing because the first derivative is negative. From 0 to 3, it's still decreasing, again because the first derivative is negative. And then it increases from 3 to infinity. Alright, so we've actually taken care of a couple of things here. We have done part A, where we found the absolute extrema. We've done part B, where we found the local extrema. And we've also done part C, where we've got intervals of increase and decrease. Okay, so now for the last two parts, D and E, we move on to the second derivative. And for D and E, we're finding inflection points and intervals of concavity. So again, we need to do the second derivative test. The second derivative test. All right, so the first thing that we're going to do is we're going to find the second derivative. Then we're going to take that second derivative and we're going to set it equal to 0. And once again, those are going to give us some critical values. And the critical values are going to create intervals for us on a number line. And we're going to do some test values to find out where the second derivative is positive and where the second derivative is negative. And that will help us determine concavity as well as inflection points. All right, let's get that second derivative. So in order to get the second derivative, I'm just going to go back to my first derivative, and I'm going to take the derivative of that. So my second derivative, I'm looking at it right now even though you guys can't see it on the screen, so hopefully you can refer back to it pretty easily. But I'm just go ahead and take that derivative, and it looks like that's what we get for a second derivative. We also want to take that second derivative and set it equal to 0 and solve to get critical values. So this is partly factorable. Everything's going to be divisible by 20x, so I'm going to factor out that greatest common factor. 2x squared minus 3x minus 3. Since I've done this problem in advance before showing it to you guys, I've already tried to factor this remaining piece inside and it's not factorable. So I did use the quadratic formula in order to solve. So this factor right here still gives me a critical value of x equals 0. But then I get two more decimal values, and again, I did use my calculator here. I know on our last exam we weren't allowed to use calculators. This time around we will be able to on this exam. So you can use calculators to get these kinds of values. Negative 0.343 was one value that I got, and 1.093 was the other value. So you may want to pause the video and make sure that you can get these two values using the quadratic formula. Or if you feel pretty confident about those skills from algebra, then you're probably all set to keep going. So we have found the second derivative. We've set it equal to 0 in order to get our critical values. Now what we're going to do is put those on a number line to find out where our second derivative is positive and where it's negative in order to get those inflection points and intervals of concavity. All right, so let's put this all on a number line. And again, this is my second derivative. You always want to keep track of what you're using. And this is the second derivative. So x equals 0 was one of my points. Negative 0.343 was another critical value. And positive 1.093 was my third. So again, this creates intervals. Negative infinity to negative 0.343. Negative 0.343 to 0. 0 to 1.93. Whoops, 1.093. And 1.093 to infinity. Alright, so we've got 4 intervals. And what we want to do is we want to choose a test value for each interval. So in this interval, there's nothing really easy to choose as a test value. And again, we can use our calculator. So I'm going to go with negative 0.5. In this interval, I'm going to go with, let's see, negative 0.1. In this interval, I'll go with 1. And then here I'll go with 2. And so what we're doing is we're taking each of those test values and we're plugging them into the second derivative in order to find out if it's a positive or a negative value. Again, I'm not going to show that arithmetic. You can type stuff into your calculator in order to figure out what you'd be getting. But I've done it in advance, so I'm just going to show you what the result is in terms of the signs. So I get a negative in the first interval. In the second interval, I get a positive, and then a negative, and then a positive. So let's interpret that. Remember, we're looking for points of inflection, and I haven't yet defined what that is. So a point of inflection occurs where the second derivative changes sign. That's a point of inflection. So basically, it goes from being concave down to concave up, or vice versa. So let's talk about concavity. So concavity is basically something like this, visually speaking, where this is concave up and this is concave down. So it's sort of like which way the graph is facing, if you will. One of my students last semester told me concave up, you can remember it using the word cup, right? Because a cup would be shaped in this way where you'd fill it that way. And then concave down is a frown. So if you think about a sad face and then a cup. Okay? So concave up and concave down. And so when your graph changes from concave up to concave down, that's a point of inflection. So for example, this is concave up, and if I change it to concave down, wherever that change occurs, that is my point of inflection. So looking at our sign chart here, we have a change in concavity right here from this interval to this interval. So specifically at this value, negative 0.343, we have a change in concavity. We have another change in concavity here at 0, and then another